Hello, everyone. It's so nice to be here and in such an enormous room, and it's so nice to see you. So my name is Patrycja Węgrzynowicz, and today I'm going to tell you about my journey to multi-active setup with three clouds, Azure, GCP, and AWS. So first, briefly about myself. I've been doing professional software development for over 20 years. Most recently, I joined Form3, and I came across to the dark side and became the platform engineer. And I must say that I truly enjoy it, even though software development is my first love. So what am I going to talk about today? So first, I would like to highlight the need to go multi-active with multiple clouds. Then I will talk briefly about Kubernetes networking. And then I will move to Cilium and its cluster mesh with what is it at all, why should we use it, and how to configure it to work properly. Then I will show you a demo of a working cluster mesh. And in the end, some pitfalls and lessons learned from our POC with Cilium. Why do we need multi-cloud connectivity? To give you a little bit of more context, I'll tell you about Form3, the company I work for. So Form3, in 2 words, is a financial cloud. So basically, it's a UK-based company which provides a payment platform for financial institutions. Basically, it integrates multiple payment schemas and provides easier-to-use API, REST-based API to their customers, making integration much easier and most of all, much quicker, so saving time and money. Technologies we use at Form3. So basically, we are a cloud-based company. At the moment, our production systems work in AWS. That's a set of microservices written in Java or Golang. And we treat infrastructure as code almost as a religion. So we terraform everything. You can imagine that when it comes to payments processing, that's really a challenging business. So first and foremost, we need very high reliability and durability. So there are some contractual obligations and SLAs written down in our contracts. So any outages or errors must be handled without any loss of data. So that's our primary concern. Plus, we need to take into account volume of payments, plus the ease of maintenance for our platform. So those are the most important factors. And when it comes to clouds, how does it look like? Let's take a look at top 7 cloud outages last year. That's the list combined by techgenics.com. So let's take a look at this and think about how many of you have been hit by any of those outages. Raise your hands, please. A few hands raised. Yeah, I don't say that's good, because that's bad, actually, right? I was hit by number 4. And actually, maybe it was not that critical, because besides my regular job, I also teach at Warsaw University. And that was just a Discord server which we had with students to provide some remote consultation or exchange some messages. So Maybe not top priority, but still we noticed that. So that's why we are going multi-cloud. At Forum 3, we are building a new platform, new payment platform, with all those high features like high availability, resiliency, scalability, performance, and most important, security. So the platform is going to spread across 3 clouds, AWS, GCP, and Azure. We are using cloud-agnostic technologies. We don't want to be bound to any cloud-specific services, or at least at a minimum possible way. So we've chosen Kubernetes with Cilium as Kubernetes CNI, and on top of that, we deploy NATS as a messaging system and CockroachDB as a database. So I'm going to tell you about Cilium. But before we go to Cilium, we need to learn more about Kubernetes networking and how Kubernetes network model looks like, because those are very important constraints or requirements for Kubernetes CNI. First of all, Kubernetes network model introduces IP per pod requirement. So every pod must have its own unique IP, and it's a cluster-wide IP. So other pods can connect to any other pod using their IPs. In theory, well, in practice as well, it looks like pods are very similar to virtual machines. So that's a clean model, and it makes a move from virtual machines to some container orchestration a little bit easier. I won't say that's a piece of cake, but at least a little bit easier. So the idea is that there is no need to deal with mapping container pods to host pods, so we are avoiding a lot of burden. Moreover, it's important that those pods communicate without any NAT, and that all agents can communicate with all pods on that node. So that's an example of an overlay Kubernetes network. Overlay because with those Kubernetes requirements for networking, you can implement different Kubernetes models, different networking models. You can have overlay network, or you can have overlay means like encapsulated. So we built another network on top of our host network. But also there are CNIs which provide an encapsulated network, which works basically on the same level as a host network. So basically here we see that on one node we have a pod with 3 containers. This pod has virtual Ethernet assigned with IP. It goes through Eth0 interface on the host node, and then it goes through router and it can be routed via host network to another host and another pod on this other node. So basically, overlay and encapsulation means that we encapsulate our source and destination IP inside another packet. On the other hand, so that's the Kubernetes model. And also when you talk about Kubernetes, you hear something like CNI, Container Network Interface. Container Network Interface is a project introduced by Cloud Native Computing Foundation. And it's a framework to configure networking resources, containers, and container orchestrators. So basically, that's not Kubernetes specific. It serves much broader purposes. But as Kubernetes is the most popular container runtime orchestrator, so that's common that we connect CNI with Kubernetes so often. CNI is plugin oriented, and its responsibilities include network connectivity of containers, provisioning IP addresses, and most importantly, garbage collection of resources. So Kubernetes implements CNI, and on the other hand, you need CNI plugins to implement Kubernetes network model. We have a broad set of Kubernetes CNI plugins, starting from cloud-specific CNIs, like AWS, Google, Azure. All three clouds provide. There are managed Kubernetes deployments together with cloud-specific CNIs, just to make networking available. On the other hand, we have third-party CNIs which can be configured in any Kubernetes deployment or any CNI compatible orchestrator, like Calico, Cilium, Planel, Weave, etc. So Cilium is a Kubernetes CNI plugin. So we've already agreed that Cilium is a CNI plugin. And how does it differ from other plugins? Their selling point is that they use eBPF. So basically, eBPF is like dynamic insertion of your custom code into Linux kernel to hook to some events, like networking, in our case. So their selling point is that because of eBPF, they're super fast. We'll see that. Then they provide extra services. Extra services like security, so network policies with advanced L3, L4, and also L7 filtering. And one of the most important features is load balancing and service discovery. So I will explain in details how it works. So basically, you can connect multiple Kubernetes clusters into a single cluster mesh with Cilium. So on top of pod-to-pod connectivity, on top of encryption, which Cilium provides as well, on top of network policies, you can also have like global service, which is load balanced across all connected clusters. And the implementation of such a service is very simple. Because that's like a regular Kubernetes service with extra annotation, global service true. So we'll see how it works. I've already mentioned that with network policies, Cilium operates with L3, L, and L4 layers, so basically TCP/IP, but also with in L7, so it can filter HTTP traffic, for example. So that might be very useful for some services which require like extra security configuration. Moreover, in terms of securities, Cilium provides encryption for the traffic inside a cluster or cluster mesh. The encryption is done using IPsec or WireGuard, so those are two different protocols. And when it comes to pod-to-pod connectivity, it provides two network models: overlay, tunneling with VXLAN or GNIF, and direct routing, which basically is an encapsulated model with routing on the host network. I've already mentioned that tunneling means that we encapsulate all network packets emitted by pods. Obviously, it introduces additional overhead, but on the other hand, we have less requirements on the underlying network. So we don't need to configure pod-to-pod connectivity on the host network. Cilium supports two protocols, VXLAN, which is very popular, and GNIF, which is not that widely used. With direct routing, network may require host network may require extra configuration. However, when it comes to clouds, it turns out you get it for free, because in clouds you've got pod-to-pod connectivity just out of the box. What are the use cases for Cilium? So obviously, high availability. So you have a backend service, and you can balance it across several clusters. When one cluster goes down, the other picks up and serves requests. But pay attention, that's load balancing only for backend services. So if you need to load balance front end, you need some extra configuration in front of your clouds. Another use case is a shared service. A shared service in one cluster, which is used by other services in other clusters. So instead of configuring load balancer, we can just have a global service and expose it in all the clusters. Another use case is like splitting stateful and stateless services, because it's from the operational point of view, that's a different characteristic. Stateless cluster, immutable clusters are much easier to manage. On the other hand, stateful clusters need extra care in rollouts or deployments. So it might be useful to split responsibilities and use several Kubernetes clusters to serve different purposes, with stateful cluster with a global service providing like data store, database service. When it comes to cluster mesh architecture, basically in each cluster, you have cluster mesh API server. That's a service. And in each cluster, you have a daemon set Cilium agents. So Cilium agents, it's a daemon set, works on node level, and it updates cluster mesh API server with up-to-date information. On the other hand, cluster meshes from other clusters connect only in read-only mode to cluster mesh from another clusters, and they read those data. So data exchange is that we write locally and read remotely. And unfortunately, that's like a full mesh. We have a full graph here. So each cluster is connected with each other. Obviously, there is the limit for scalability in such an architecture. But when it comes to configuration details for each cluster, we need to know all other clusters with cluster endpoints, that's a domain name, and a set of certificates to connect, that's MTLS connection. And each cluster domain name must be resolvable to an IP address. That's another drawback, because when you think about cross-cloud deployments and cross-cloud cluster mesh, you need to provide DNS resolution in multi-cloud environment. However, that's not like a must, because there is like an alternative method of configuring cluster mesh to use host aliases. So let's take a look quickly at Cilium cluster mesh configuration. You can see that's like a secret deployed on each cluster, which contains a list of all available clusters in a mesh together with DNS names and certificates. To make DNS resolution easier, we can configure host aliases. So basically, we can base our configuration on static IP addresses and assign them custom host names. That's a patch to Cilium Agent, and Cilium Agent adds those lines to our host configuration in a given node. OK, let's take a look and see cluster mesh in practice. So how does my mesh look like? I have 4 clusters, 2 clusters in GCP and 2 clusters in AWS. Unfortunately, my Azure clusters didn't want to cooperate with me today. But still, we have 4 clusters. We've just, and the demo, oh, that's pretty cool demo, because the demo is based on Star Wars theme, and the important part is that it's based on Isovalent. Isovalent is a company behind Cilium. So that's Isovalent Cilium Star Wars demo, just slightly adjusted by myself. So we have X-Wing deployment, and we have Rebel-based service. So let's board our X-Wing, and let's see if we can reach our Rebel base. OK, here we are. And we see that the answer comes from AWS cluster number 2. That's a lot. Rebel base is a global service, so let's see if it's really load balanced. So I will try to loop over different connections to our Rebel-based service with a sleep, just to see what's going on. OK, looks fine. Yes, it looks like it's load balance, and we see different clusters here. So now let's try to take down one of the clusters. I've just switched to my AWS cluster 2. And I will scale down to 0 replicas. And now we shouldn't see an answer from cluster 2. It looks like it's Fine, so the cluster 2 went down. Let's do the same to cluster 3. That's GCP-based cluster. Scale down, and now we see only 1 and 4 in our responses. So let's take over the galaxy and let's scale down the last one. So that's the last one. And now we are seeing that form 3 rules the galaxy. But we are not that greedy. We are not that greedy. We are scaling back. OK, we are seeing GCP cluster 4 is dominating because I've increased the number of replicas. So that was cluster mesh in practice. And that looked very easy, right? But unfortunately, our journey across 3 clouds and Cilium and cluster mesh was not a piece of cake. So the very important maxim, never underestimate your enemy. So I was always thinking that RTFM, read the effing manual and you'll be fine. Unfortunately, that was not the case, and unfortunately, I think that's not the case of cloud development. You have a lot of corner cases, you have a lot of changes, and even though your plan looks simple and easy to achieve, the reality is completely different and much more like a slapstick comedy, which personally I'm not a fan of. So the first thing, we wanted to start small, Cilium CLI. They provide very neat CLI to install Cilium, to create a cluster mesh. The documentation was like a couple of commands executed, and you are good to go. Unfortunately, it didn't mention that it doesn't work with hostname-based load balancers. So with AWS, we have hostname-based load balancers, so Cilium CLI doesn't work. But that was not our goal anyway, because our goal was to have Terraform configuration for all our infrastructure. So we moved pretty easily over this issue and to terraforming our code. So preparing a cluster, preparing all required resources to install Cilium. And some Cilium fundamentals which are not very easily to be found in Cilium docs. So you need to taint or you need to rescale your node pools. Because otherwise Cilium doesn't work. It is reasonable because Cilium is a CNI. It replaces the original CNI of a cloud. So it needs to create extra interfaces. It needs to take down the old interfaces, network interfaces. It needs to update IP tables. It needs to inject some code into Linux kernel. So that's a lot of work, and it needs to be done before any pods get scheduled on a given node. So that's important to taint a node just to prohibit scheduling of any extra pod, because otherwise such a pod will become unmanaged by Cilium, and networking won't work for this pod. Another important thing is to use appropriate roles for Cilium operator for EKS. And fortunately, that's very well documented in Cilium OSS docs. Unfortunately for us, we were using Cilium Enterprise. And what's kind of surprising, Cilium Enterprise documentation is in many places much worse than OSS. Another issue we had, which was blocking our Terraform plans, especially destroying clusters and VPCs or virtual networks, was hanging resources, especially in AWS. So we encountered a lot of hanging network interfaces, but that turned out to be our fault and misconfiguration. We had delete on termination configured to true, so that's a flag to delete given network interfaces created by Cilium on termination of a node. But on the other hand, we made a mistake in our Cilium operator policy. So we misconfigured and didn't include modify network interface attribute. So basically, Cilium operator couldn't modify network interfaces, and that way they didn't have this flag delete on termination configured, and they were hanging. But as a drawback, Cilium reporting and logging is rather on the light side. So we didn't find anything in logs. It was very difficult to debug, and actually we found it by chance digging in some other parts of Cilium source code. I've already mentioned the problems with hostname-based load balancers and Cilium CLI. Basically, the problem is with Cluster Mesh API server service. That's a service responsible for meshing. And to configure the service properly together with the entire meshing configuration is not a piece of cake. First of all, the recommended type for the service is obviously load balancer. We need to connect across clusters, so it can't be cluster IP, because cluster IPs are not routable. According to a Kubernetes spec, but according to GCP, they are actually. So it depends on the cloud, but we are multi-cloud, so cluster IPs are not routable for us. So we are left with load balancer or node service type. Obviously, node service type is not ideal because it's node specific. We want to have easy failover. When one node goes down, it should be transparent for us. So load balancer is a way to go. However, we have different clouds and different load balancers available. AWS provides DNS-based load balancers. So basically, your balancer is accessible via domain name. And only this type of access provides high availability setup. On the other hand, Azure and GCP, they provide IP-based load balancer. So you can hit your load balancer by IP and still it's HA setup. Obviously, I mentioned that for cluster mesh API servers, we need those host aliases. We need those host aliases. We need to think about static IP addresses versus dynamic IP addresses. When we want to use static IP addresses, we we are good to go with host aliases. Otherwise, we would need to monitor and constantly change whenever an IP of a load balancer changes. So that's one problem, static versus dynamic IP addresses. On the other hand, we have multi-cloud DNS. So we would like for secret-based configuration, we would like to have resolvable domain names for our cluster mesh API servers. So our first approach with static IP addresses and host aliases seemed the best way or the simplest way to go. On GCP and Azure, it's very easy to assign a static IP for your load balancer service. So you just add load balancer IP to your service spec. On the other hand, it's a little bit more complex for AWS. You need much more annotations, but that's still doable. The one of those annotations maybe does not address exactly static IP addresses. This one, the cross-zone load balancing enabled. But that's very important for your cluster mesh API servers, because by default in AWS, your load balancers only hit pods services in the same availability zone. So when one zone goes down, your load balancer responds randomly as service down or correct response from other zones. So to have a consistent, reliable behavior, we need to enable cross-zone load balancing. However, when you have static IP addresses and you have your IP addresses management, you need to think about collisions. Because you can't just pick one random IP from your subnet. Because you can end up with a collision, for example, during some restart rollouts, this IP can be taken by a node or by a pod or by a service, and other load balancer service. Usually the way to solve this kind of issue is to use a dedicated subnet or reserved pool of IP addresses, depending on a cloud. Dedicated subnets work across the clouds. While in GCP, as far as I remember, in GCP you can reserve a pool of IP addresses in your network, so that may be a little bit easier configuration. So we've already solved our static IP addresses, but what about host aliases? Maybe host aliases are not the best approach and production-ready approach. Maybe it would be better to use actually DNS and configure our cluster mesh services through DNS. But then we need to think about how to expose our load and configure our load balancer cluster mesh API server service in DNS. It can be easily done by using external DNS. That's a simple one extra notation to a service. And external DNS propagates those records to cloud DNS. But then we need to exchange those records across multiple clouds. So we need to configure kind of multi-cloud DNS when one cloud resolver forwards domain names to be resolved to other clouds. We can do it basically by assigning cloud-specific zone to a given cloud, for example, aws.example.pl, gcp.example.pl, and the same for Azure. And in each cloud, we need to have forwarding zones that forward the traffic to the corresponding resolver. Our another approach was with Core DNS because we are very eager to mesh and configure multi-cloud cluster for our NAS service. And we are behind with our cluster mesh configuration. So we configured Core DNS to work in a multi-cloud setup. Unfortunately, it works only in Kubernetes clusters, and it must be done via Core DNS because GCP doesn't support configuring kubelet domain name. What was our experience? Does Cilium provide what it promises? It provides something. eBPF lightning speed, not in clouds. Unfortunately, in clouds, eBPF is not used to the full of its capabilities because Cilium doesn't support eBPF host routing in clouds, so we still have legacy routing. And comparing performance results from cloud-native CNIs and Cilium, those are, I think, the same. The difference is like half millisecond, so that's nothing. Pod-to-pod connectivity, yes, obviously it provides, but on the other hand, cloud-specific CNIs, they provide it as well. Load balancing and service discovery, yes, it works, as you had a chance to see during demo. On the other hand, for production setup, it might be not the optimal solution. Why? Because they provide only a very basic kind of round-robin load balancing, so no way to configure some sort of affinity towards local cluster, for example, or more advanced policies to implement, for example, canary deployments. On the other hand, they are working on that, but they've been working on that for over 2 years. Network policies, that's a very cool feature because not only L7 filtering, but also identity-based service-to-service communication. So we can have separate security domains inside our cluster or cluster mesh. That's very useful. And that's definitely what we are going to use. On the other hand, L7 filtering, first of all, it didn't work for us in tunneling mode. And second of all, which is even more important, it works in 99% of cases. So we have domain name-based filtering configured, some egress traffic to the public internet based on a domain name. And it works in most cases, 99%, but sometimes packets are forwarded. So when you are in a payment business, you can't afford for such a mistake. Encryption. When it comes to encryption, yes, it works. However, our InfoSec team discovered it works only across nodes. So the traffic inside the same node is not encrypted. And that's by design. So again, that's a no-go for us because we are in a payment business. However, for less critical system, it might be a good enough solution. And that's only the top of the iceberg because when it comes to Cilium, you have a lot of configuration knobs. Cilium has like hundreds of parameters, and to get familiar with all of them and to see which configuration set of parameters actually works and which doesn't, it takes a lot of time. Debugging networking in the cloud was pretty fun, I must say. TCP dump to your rescue. On the other hand, we experienced a lot of surprising and unexplainable behavior, like unmanaged pods. With unmanaged pods, you end up failing pod-to-pod connectivity. Fortunately, they told us that was fixed in version like a month ago. So we'll see, we'll test that one. We also saw a lot of version incompatibilities. So, for example, Amazon images were not compatible with our Cilium version. We had to wait until they released a new one. Cilium didn't support Kubernetes 1.22, which was the new one in GCP, and in GCP you can't control your Kubernetes version. So when you work multi-cloud, you see a lot of such surprises and blogs. So that's a given. However, it's quite challenging work, and it gives a lot of pleasure to see it finally working. So remember that, unfortunately, our tools are not smarter than we are. And on the other hand, a fool with a tool is only a fool. So we need to use our tools wisely. And before you start using Cilium, especially Cilium Cluster Mesh, ask yourself whether or not do you actually need it. So you need to know your business use cases. You need to know your tools and experiment and test, because that's not going to take you like a month. We've been working with Cilium for personally from August last year, and I still don't feel an expert on this one. So a lot to learn. And I heard that someone said that as IT and software development, we are very fashion-oriented industry. So we follow the freshest trends. Don't do that. Don't follow the fashion. Take a look at your use cases and take a look at what tools actually support your use case. So thank you very much. Any questions and comments? I think we are running out of time, but I'm open to stay with you during a break and answer all your questions. Thank you.